Hello, my name is Thorsten Eisenhofer, and first of all, thank you for taking your time today and joining me for this presentation. In the following, I want to present to you our work Dompteur on the defense of audio adversarial examples. This is joint work with my colleagues from Ruhr University Bochum in Germany and the University College London. Before I get into detail of our construction, let me briefly explain the background of audio adversarial examples and motivate our research. By now, voice interfaces are everywhere, whether at our homes, cars, or in our pockets. It is predicted that by 2024, the number of digital voice assistants will reach up to 8.4 billion, a number higher than the world's population. At the core of these assistants lays a system for automatic speech recognition, which in turn is based on machine learning and in particular neural networks. Given an audio signal, the task of the ASR system is to transcribe any spoken content.
Bids totaling $651 million were submitted.
In such a scenario, an adversary's goal might be to disturb the input in order to fool the system into transcribing arbitrarily target transcriptions or mounting a denial of service attack which will cancel out any transcriptions.
Bids totaling $651 million were submitted.
Note how barely noticeable the distortions are in this case, though the system is fully convinced to understand something completely different. There are many theories what causes adversarial examples, but so far not a single explanation could be found that fully captures the observed behavior. Nevertheless, there are several interesting observations. Specifically, when training such a system, it will use any available signal to solve the task at hand. In the end, it's all data for a neural network, and the network does not have any priors. Second, there are latent structures in our datasets that we also show in our experiments, which are highly predictive, yet not directly observable by human listeners. Combining these two ideas, adversarial examples are the result of a mismatch between human expectations and the working of our systems. In fact, assuming a realistic attacker, it is always possible to construct valid adversarial examples. In the worst case, the attacker just needs to adjust the complete input. Therefore, we are asking the following questions. When we accept that adversarial examples exist, what else can we do? Our goal in this work is to align our systems better with human perception. In other words, even though we cannot prevent audio adversarial examples completely, at the very least, we want to make them noticeable. In this case, any attack, although still viable, is losing most of its malicious impact. For Dompteur, we base our construction on the field of psychophysics, pioneered by the psychologist and physicist Gustav Fechner during the 19th century. In particular, we are interested in the subfield of psychoacoustics, which allows to describe limitations of the human auditory system. Consider, for example, the absolute hearing thresholds in quiet. These indicate, as a function of frequency, the sound pressure level of a pure tone that is just audible. Generally speaking, everything above the thresholds is perceptible and everything below is not. Moreover, much more energy is required for a signal to be perceived at lower and higher frequencies. Besides the human hearing thresholds in quiet is the presence of another sound, a so-called masking tone can change the thresholds to cover a larger area. In this example, a loud tone at 1 kHz shifts the hearing thresholds of nearby frequencies. Like frequency masking, temporal masking is also caused by other sounds, and more precisely by the fact that the auditory system needs a certain amount of time to recover after processing a loud signal. This effect does not only occur at the end of a sound, but also at the beginning of a sound, though much less distinct. This seemingly looks like a contradiction at first, but can be explained by the mechanical processing of sound in the human auditory system. For a given audio signal, all of these effects can be summarized by psychoacoustic hearing thresholds. These thresholds define how dependencies between certain frequencies can mask other parts of an audio signal. Intuitively, these parts of the signal should not contribute any information to the recognizer. They do, however, provide space for an attacker to hide adversarial noise. Based on this, we derive a mask to remove parts of the audio that are inaudible. Specifically, we filter an audio signal S, given in its frequency representation, by multiplying it with this mask.
Bids totaling $651 million were submitted.
Note that the filtered signal basically sounds unmodified as we only remove inaudible parts. By adding a parameter phi, we can even control the effect of the hearing thresholds. For values greater 0, we use a more aggressive filtering, and for smaller values, we retain more from the original signal. Consider, for example, the case when we set phi to 12. As can be seen in the plot, we will now filtering much more of the original signal.
Bids totaling $651 million were submitted.
Again, even for this high value of phi, the spoken content is still clearly understandable. And during our experiments, we show that for higher values of phi, we gain stronger robustness, but simultaneously incur a robustness performance trade-off. Finally, as the human voice frequency range is limited to a band of approximately 300 to 5000 Hertz, and we are interested in transcribing spoken content, we also add a bandpass filter to further reduce the attack surface. Based on this augmentations, we implemented a prototype for Dompteur for the open source toolkit Kaldi. Kaldi itself is used throughout the research community as well in commercial products like Amazon's Alexa. In order to augment Kaldi, we add the psychoacoustic filtering to its pipeline and extend the feature extraction of the neural network with a bandpass filter. Given these augmentations, we can then train an augmented model, which will focus to use only audible ranges from the input. In order to test our construction, we considered the following experiment. In this experiment, we have two systems, a baseline Kaldi system and the corresponding augmented Dompteur version of it. For benign input, Kaldi has a small error rate measured as a mismatch between the prediction and the ground truth. In this case, it's 5.9%. Feeding the equivalent filtered input to the augmented system, we obtain a similar error rate of 6.1%. Such a drop is expected as previous research already indicates that adversarial robustness is generally correlated with a loss in accuracy. More interestingly, though, is the case when we feed standard input to our augmented system. If Dompteur does indeed learn a better model of the human auditory system, it should retain a low word error rate even when presented with non-filtered input. Again, the word error rate only drops slightly to 6.33%, thus the model has learned to ignore unnecessary parts of the input. Kaldi, on the other hand, heavily relies on this information when transcribing audio, increasing its word error rate by over 2.8% when fed with the filtered input. To analyze adversarial robustness, we constructed a strong white box attack against Dompteur. As expected, attacking Dompteur is much less effective, but ultimately the attack succeeds to construct valid adversarial examples. However, in this case, we find that adversarial examples are of poor quality and are easily distinguishable from benign audio and adversarial examples constructed for the baseline system. We further substantiate these claims with a large-scale user study with over 350 participants. Finally, I want to present to you an example of the computed adversarial examples. First, the adversarial examples from the beginning, which was computed against the unmodified Kaldi baseline system.
Bids totaling $651 million were submitted.
And the equivalent version against Dompteur, which was trained with a parameter phi set to 12.
Bids totaling $651 million were submitted.
As you can see or hear, the adversarial example is much more distorted than the counterpart for the unmodified baseline system. In summary, adversarial example seems to be inevitable. Therefore, we propose a different perspective, and instead of preventing all adversarial examples, we accept the presence of some, but we want them to be audibly changed. In our paper, we showed with Dompteur that psychoacoustics are an effective tool for this task in the case of audio adversarial examples. Thanks again for your attention.